Okay, so everybody, well, welcome back to the String Fino seminar series. For the first talk today, we're very happy to have Vincent Menet from Milano, who will be telling us about new results on AdS, vacuum decay. So please take it away.
All right, thank you. Thank you for the introduction. And also let me start by saying thank you to the organizers for the invitation. I'm happy to speak here today. So indeed, I'm going to talk about AdS vacuum decay. So you might be wondering, why is that even interesting to think about the possibility of the stability of AdS vacua? And the motivation actually lies behind the weak gravity conjecture that has been formulated 20 years ago. It is something that has been discussed at length now in the literature. There are many different ways to think about it. But there's one way to put it, which I think is a good way to start for today, which is to say that this actually conjectures that the mass of a given particle, which is carrying a given unit of charge, has to be smallest than the smaller or equal to the mass of the corresponding particle if it was an extremal black hole. It's nice to put things in this way because, of course, first of all, it connects to black hole argument, right? Just saying that a black hole has to be able to emit particle in decay. And in that way, it actually connects to other conjectures as well. But most importantly for today, it actually very naturally generalizes to other objects other than particles. You could think of any extended object and basically make the same statement. For instance, you could make a version of the conjecture for now branes, and you would say the same thing. You would say that now the tension of a brane that is carrying some unit of charge has to be smaller than the tension of the corresponding brane if it was an extremal like brane. So it's a very straightforward generalization, as you see, but it's well less physically motivated, right? In the sense that you're losing the connection with black hole physics. So you might be wondering whether or not that version of the conjecture is actually correct. And also, it does sound like an innocuous generalization, but it actually goes a long way. Well, it actually has important physical consequences, which I'll come back to now. But in order to do so, let me just mention that this conjecture also says that about the equality. So when the tension of the brane equals the extremal value of the tension, the conjecture actually says that this happened for supersymmetric solutions, and the corresponding brane has to be BPS. So this is the part actually of the conjecture that has strong consequences, because it is saying that for non-supersymmetric solution, let's for instance say here of AdS, non-supersymmetric solutions have to have at least some branes that have their tension to be strictly smaller than the extremal tension. So let me not go into the details now. I will do so in the bulk of the discussion. But let me just say that branes that behave in that way are actually responsible for the vacuum decay of the vacuum they're embedded in. So the message I'm trying to convey here is simply that that version of the weak gravity conjecture implies that non-supersymmetric AdS solutions have to be unstable. And well, if you're caring about flux compactification, this is a fairly comfortable situation to be in a way, because if you were to try and go against the conjecture, you would simply have to find a single example of a stable non-supersymmetric AdS solution, and that would disprove the conjecture. So many people have tried to do that, including the people that I'm listing here, and I am sure that I'm forgetting some. But for now, there hasn't been like a rock-solid, rigorous example of a single stable non-supersymmetric AdS solution, at least in type 2 string theory. And the reason for that is that it's actually kind of challenging, because in type 2 you have different charges, and to these different charges are associated many different brane configurations. You could have D-branes and S5 branes, bound states between them, or more exotic branes. And it can be a bit hard to keep track of what are the charges and the way the corresponding branes are behaving. And actually, even if you focus just on D-branes, in full generality, you have a large variety of possible cycles that D-branes could actually wrap. So it's even challenging to just make a general statement about D-brane for some AdS solution of type 2 supergravity. Okay, so from my, I admit, maybe limited understanding of the literature, I have the feeling that the decay channel, I mean the decay mediated by branes that are studied mostly in the literature, are treating D-branes and not so much the bound state that they can form together, because it's harder actually to make a scan for D-brane bound states in general. And also the branes that are usually discussed mediating decay are abelian branes. Again, also because it's significantly harder to talk about non-abelian branes in general curved background. So these are the two aspects that I would like to talk about today. The first one is a strategy to try and be a bit more systematic in the treatment of D-branes and their bound states in AdS solution. And the second one, as I was saying, is a decay channel that would be mediated by non-abelian branes. So both results I'm going to talk about now have been found in collaboration with Alessandro Tomasiero last year. All right, so about trying to be a bit more systematic in the treatment of D-branes and their bound state, let me now just be a bit more precise about the specific decay process that I've been talking about. So throughout this discussion today, I'm focusing on AdS solution of type 2 supergravity. So we're considering an AdS solution, and inside of it, we're considering the nucleation and expansion of a brane that would be a domain wall in AdS, a spherical domain wall, which would expand in the radial direction of AdS. That domain wall would be charged under a given charge of the theory. And as it would expand, it would discharge the fluxes corresponding to the charge that the domain wall is charged under. So it basically replaces the old AdS vacua in which it's embedded with a new vacua that the domain wall encloses. All right, that's from the AdS perspective. From a 10-dimensional perspective, that domain wall brane can wrap whatever internal cycle it wants in the geometry. And also let me mention here that I'm only considering branes that are probes, so neglecting the back reaction of the geometry for all of the discussion today. Right, so the one thing you could ask yourself is what could be, for instance, in a given AdS solution, what could be a condition to be safe against this nucleation and expansion of a brane, so against that process. So for a given brane, if you would like to do that, what you have to do is look for the condition of existence of a spherical instanton in AdS. And if you want to be safe against this decay process, you would simply say that the corresponding brane needs to have its charge to be smaller than its tension. There's a very intuitive way to think about it. If you think about the charge of its contribution in the brane action, it's a contribution that wants to make the brane expand, whereas the tension is a gravitational contribution that wants to make the brane collapse onto itself. So I'm just saying that if you want to be free against this decay process, you just need the contracting force to be winning over the expanding forces. That's it. So as I was saying, in 10D, you can think of that domain wall as wrapping some internal cycle, sigma. In that case, you can specify that bound I just wrote. It's a very standard procedure. You just write down the action using the Chern-Simon part of the brane action, and the tension is related to the dBi action. And you get the following bound. So again, if you want to protect your AdS solution against the nucleation of a brane wrapping sigma and also with worldsheet flux calligraphic F, you would just need to evaluate that bound, and that's it. It can be not that challenging to evaluate that bound for some given configuration, but where the challenge actually becomes when you're trying to make a general statement about an AdS solution, and you would need to, for instance, evaluate that bound for every possibilities of cycles and worldsheet flux for your geometry. So this is really where the core of our method comes about, which is that we're taking advantage of the fact that you can actually bound the dBi action from below here. So I will not so much, I will not talk into details about how that bound comes about. It's a standard result of calibration theory, where psi here is just a polyform in the internal geometry. I'll just say one thing. This bound exists whenever you can think of this polyform as being a bilinear in some internal spinors. Okay, at this level, it's a bit abstract, but I will apply it to a specific concrete AdS solution, hopefully, and I will give you the form of the polyform psi, so it will hopefully become clearer. But now we can come to the good news, which is that instead of comparing the charge and the tension, we can compare the charge and now this estimate from below for the dBi action, which is actually significantly simpler to deal with. So out of this, we can devise now a criterion aiming at the stability of a given AdS solution against the nucleation of a brane that would be wrapping, again, the cycle sigma. So here what I'm doing is no mystery, right? I'm just pushing this now estimate from below of dBi, this integral on the other side, and devising now and writing down this quantity R just for ratio, and saying that it has to be smaller than 1 in order to be safe against this decay process. This ratio R has nice properties because if you think about it, well, the numerator coming from the charge, the integrand is closed. This comes from the Ramond equations of motion. But the point here is that it can also be the case of the denominator if you're smart enough in the choice of psi, which I will try to make more precise in the example. But yeah, you might be able to make a choice of psi such that the denominator is also closed. So all in all, when you do that, your quantity only depends on the homology class of sigma. It doesn't care about the specific representative that you're picking. And that's a comfortable situation to be in if you want to try to scan large varieties of cycles and well-sheet flux. Then a bit more practically, this ratio, what happened when you try to evaluate for a given AdS solution is that as you see, the structure of the integrals are similar, right? It's a polyform wedging e to the minus f. So you have large chunks of these integral that factorize and drop out, and you end up with nice quantity R that you can evaluate and compare with one. Okay, this is all just to try to convince you that this is a nice criterion to try and aim for, like scanning a large varieties of possibilities for D-branes and their bound states. But here it's important to stress that this is only an argument for stability. We're devising a strategy to aim for the stability of an AdS solution with that criterion. But if it fails, we're entirely in the dark. We are not comparing the charge and the tension anymore. We cannot really conclude anything about the vacua if our criterion fails. All right, I think this is everything I wanted to tell you about the method itself. So now I'll try to illustrate it with a simple solution. So which is what we have done with considering massive type 2a solution in the form AdS4 times CP3. So this is a one parameter family of solution. And the one parameter is simply the relative size between the base and the fiber of CP3, if you consider CP3 to be an S2 fibration over S4. And so it has been shown by these people that that parameter actually lies inside this interval here. And for every given value of the squashing parameter, you have several solutions. Some of them are supersymmetric, some of them are not. All right. Then, well, using the two Kähler structures on the spheres, you can write down using their Kähler forms, you can write down an SU3 structure in CP3. And ultimately, this is actually what provides you an ansatz for the polyform psi, because that polyform can be seen as a bilinear in some spinors. But then here you have some freedom in the choice of here. I just put an angle theta, and you have some freedom here. And let me say that in some instances of the calculation of the ratio R for some given brane, we actually had to fine-tune the value of theta such that we could enforce the closure. So this is just to illustrate what I was saying above, saying that you have to be a bit careful about the specific ansatz you make for your rough estimate of dBi from below. Okay, I can now tell you what I'm plotting here. So the thing that I'm plotting here is well, that for every specific dot that you see on the plot, this corresponds to a given vacua. And for every given vacua, what we have done was to calculate this ratio here. But for every possibilities, for D2 branes, D4, D6, D8, and bound states between these, specific bound states using the only closed two forms that there is in the bulk of CP3, which is in our conventions, the one you see here on the screen. And so what we have done, once we have calculated all of these ratios, we just collect them together and we select the maximal value because that's the only thing we care about, is that all of the ratios would have to be smaller than 1 in order to reach a conclusion for stability. So we're looking at the value of the maximum of these ratios, and it suffices that this one would be smaller than 1. So as you see here, for some solutions, we have some red lines where our method is inconclusive. We cannot say anything about these vacua, but we also have some black lines that corresponds to vacua where our strategy has worked, and we have shown that these are safe against the decay mediated by any D2, D4, D6, D8 brane and their bound states, which is really nice. But there's a big caveat here, which is the fact that using this worldsheet flux for the bound state is fine for D4, D2 bound states, for D8 bound states. But in the case of D6 bound states, they could be something more in the sense that D6 bound states in AdS4, they would have to wrap a 4 cycle inside of CP3. And these could have additional closed 2 forms. So these could, correspond to other worldsheet flux, and associated to them could be other bound states, D6, D4 bound states, that we are not treating here. So this is an incompleteness in our approach. So we are very close to a complete scan of branes and their bound states, but not quite entirely there. Okay, so the reason why I chose to show you this example, it's not the nicest that we have found, because we have scanned now for a variety of AdS4 and AdS5 solution, but it's the cleanest, quickest way to illustrate our method. And also it's nice because it sort of shows what we have witnessed for every other solution, which was that we were always close from making a complete classification of branes and bound state, but there were always just maybe sometimes some situations that we couldn't quite capture with our method. We have some examples that are better in terms of stability result than this one. I leave you to look into it if you want. These are AdS4 times Kähler-Einstein 6 more general solutions. Okay, I think this is everything I wanted to tell you about abelian branes. Every brane that I've been talking about here and their bound states were abelian. So let me now move on to non-abelian branes, and by that I just mean allowing for the branes in a given stack to now interact together. This is what I mean by non-abelian. And the reason for that is because in practice, if you want to do that, if you want to allow interactions between the branes in the stack, you would have to allow the transverse direction of the world volume of the brane to now be matrix valued in the UN algebra, which would be defined by the stack of n D-brane. So this is what Myers has done in 99. So I'm just flashing the actions here. I don't want to go into too much details. But the way he's done it was basically to consider the 9 branes, which do not have any transverse directions, and then TDualize carefully all the way to the general case. So as they're written like that, as it's written like that, the brane action, it's not yet entirely useful, because if you think about it, every field that enters this action, the metric, the B field, the potentials, they all, in full generality, nothing prevents them from depending on these transverse scalars, right? And so if you want to evaluate the brane action on the world volume of the brane, well, you would have to Taylor expand to a certain order, now in this matrix valued object, so you have to do it carefully. Myers proposed a prescription to do that, and he actually he has done that to a certain order, but he has done that in flat space. He has done that expansion in flat space. We did it in full generality, so he wrote down the full expanded action in curved space. But the thing is, the action then it's a bit lengthy and complicated. So we decided then to treat only a specific case by adding a restriction requiring the scalars to be constant over the world volume. And in that case, then the action simplifies tremendously, and you can write down the equations of motion in a nice and compact way, and you can study their solution, which is what we have done at that level of generality. But when it comes to these equations of motion, ultimately you don't have a these as subalgebras of of UN, you only have the reductor living inside of the 10D of string theory, so you cannot you don't have a lot of possibilities. You could, for instance, have 3 non-trivial scalars that would cook up together the generators of SU2. You could have 6 of them cooking up the generators of SU2 plus SU2 and 8 for the generators of SU3. That's essentially the 3 possibilities. Okay, so we have solved these equations of motion, but now for the specific branes of interest for today's discussion, which are, again, coming back to domain walls in AdS. But here only pure domain walls in the sense that they don't wrap any cycle in the internal geometry. We focus on this case here. Then if you add the requirement that the warping and the dilaton are constant, you end up in a nice situation in the sense that the equations of motion trivialize in the case of an SU2 algebra, and you always have a non-abelian pure domain wall that exists with the following charge and tension. As you see, the charge does not change, and the tension is modified by a term that is sourced by the H flux. This is essentially analogous of what Myers finds in flat space. For the case of SU2 plus SU2, now the equations of motion are complicated. We have not solved them generally. We have again made an assumption. We have imposed that the H flux would have to be a sum of 2 contributions with independent support. And once you've done that, again, you have the trivialization of the equations of motion. And you always have a non-abelian stack with the following charge and tension. As you see here, we're stacking together 2 SU2 contributions that do not really talk to each other. All right, and briefly.
You have 3-4 minutes left.
Okay, good. Yeah. So let me briefly say that for SU3, we find the possibility very unlikely because the equations of motion would impose the H flux to be proportional to the SU3 structure constant, which seems very unlikely. All right. So one thing I want to convey here is the fact that the tension reduces, which is very nice because it makes the brane less self-attractive. So it could open up a new decay channel in the sense that the brane could a given AdS solution could be free against the nucleation of abelian brane, but then non-abelian branes could actually still trigger the decay of the solution. This is what we have shown as a proof of principle for a given solution, AdS3 times S3, S3, S1 in type 2b. We have shown that the pure abelian domain wall D1 were not mediating the decay, whereas their non-abelian analogs were. I want to stress here that this is a non-abelian, this non-abelian channel is a small channel in the sense that the contributions here entering the tension are very small, the one that reduce the tension because of the way the string length and the flux enters. So this non-abelianness becomes only very relevant when you're close to extremality for the abelian brane. So Q equals T. Okay, and finally, let me just mention that you can remove the constraint on the triviality of the dilaton and the warping. Now the equations of motion are non-trivial. As you see here, they relate the H flux and the eigenvalues of the Haitian of a combination of the dilaton and the warping. But once you solve these equations of motion, you have exactly the same non-abelian brane configuration I just showed you. Okay, I think this is everything I wanted to tell you. Let me quickly wrap up. So I've been trying to introduce today, a strategy to be a bit more systematic in the treatment of the decays mediated by D-branes and their bound states. As I told you, we haven't been entirely successful in finding a bulletproof, stable AdS solution. Maybe people can be smarter than us in applying our method and aim for that. We also found some new non-abelian domain walls in AdS. They have the nice property of being less self-attractive than the abelian ones. So I've been trying to convince you that they can actually change the conclusion you can reach about the stability of a given solution. Finally, 2 quick perspectives. Of course, an obvious one would be to release the assumption of the constancy of the scalar over the world volume of the branes. You would treat more general domain walls. I think it would have very interesting applications, for instance, to the DGKT solutions that are scale-separated AdS solutions that actually have an extremal D4 brane. So I wonder what non-abelianness can actually of that brane can actually tell you about the DGKT solutions. And the last thing I want to mention here that I haven't talked about was the possibility of making the radial direction of AdS, which is indeed a transverse direction of the brane, to actually promote it as well to be matrix valued in UN. We have shown that it was impossible to have this very exotic non-abelian brane configuration in a large class of AdS solution, but not in full generality. So I think it would be interesting to study further. All right, thank you very much for your attention.
Thank you very much for the talk, which was also perfectly on time by the second. Are there any
Cool.
questions? Yes, Hassan.
So you said that the ratio that you were studying, you said that if that ratio is less than 1, then the test says that you do have stability against the brane decay, and if it's greater than 1, then it's inconclusive. But what about if it's equal to 1?
Right. Well, if it's equal to 1, it depends how you think about it. But so roughly speaking, let's say in supergravity, this is convincing enough. You don't have, you're not triggering any instability because the brane does not have the dynamics to basically replace your solution. But this can also be kind of suspicious because these are at risk of having corrections that would actually make the brane able to mediate a decay. So I guess the answer to that question, the way I think about it, is in supergravity you're safe, but it casts some doubt on the actual stability of the solution in full string theory. Yeah.
Okay, thank you.
Thanks.
Any other questions? Well, if not, maybe let me ask, could you say a bit more about applications, which is actually I was going to ask if you, well, applications to DGKT, what are the obstacles that you need to?
Yeah. Yeah, about DGKT, the thing is, DGKT has a domain wall as well, which is extremal, which was T equals Q. So that's related to the previous question, right? What happens when you're at extremality and you're and so this is precisely the place where it's very interesting to think about corrections. I want to mention here that Miguel Montero and Irene Valenzuela have thought about this before, about correction to the extremality of that brane, quantum correction, and they saw that it was spoiling the extremality. What I'm saying here is that very hypothetically, I want to talk here about, well, these are stringy corrections, right? The corrections of the non-abelianness in a sense, because they have some string length that enter the discussion. And I'm guessing that this could also spoil the extremality of the domain wall of the GKT. And the thing is, in order to treat that, you would need to treat these more general domain walls. So you would need to release this constancy of the scalars assumption in order to see whether or not that extremality of the domain wall is also spoiled by stringy correction, just as it was for quantum corrections, as it was shown. But here, I think it would have strong consequences on the GKT because it would trigger a decay of a supersymmetric solution, which would indicate that there's something pathologic in the supersymmetry of the GKT. It could actually be that the solution is not a supersymmetric solution of string theory. I want to stress here that this is very hypothetical because you would, in order to be able to talk about this domain wall, you would need to release that assumption. So I'm just guessing that if you have a similar way to behave for domain walls than the pure domain walls here, but also for the domain wall that are wrapping some cycle in the internal geometry, this would have this consequence for DGKT. This is really hypothetical, right? It just yeah.
Thanks.
Thanks.
Any other questions?
Sorry, Vincent. This is your collaborator. So you mentioned that we were not quite successful with the stability issue. Certainly, this is so for AdS4. For AdS5, things were a little better in that respect, right?
That is very true. In terms of
we usually don't stress this, and because we are fixated, maybe we are fixated on AdS4, but
No, it's of course a very good point. The reason why I didn't choose to talk about these, we have some AdS5 solutions that are free against the decay mediated by D-branes and bound states, but I think these are the ones that have been shown to be at danger when it comes to the possibility of the bound state with NS5 branes, and I think some people have made the claim that it was actually unstable against that decay. So this is why I thought it was a very nice example for some charges of the theory, but not for others. So that's why I chose.
Okay, fair enough. So we succeed, but others fail.
Yeah, we succeeded and we
Okay.
failed, and because of the 25-minute format, I was like, okay, let's put that
Sure,
example on
yeah.
the side.
Perfect.
Yeah.
Perfect.
Okay, then if there's no further question, we can thank Vincent again and go on to the next speaker.
Thank you very much. Thank you, guys.